Welcome to MEPKBT College of Engineering. Myself, Dr. Kadam MP, working as a head and professor of Civil Engineering Department. So today we're going to discuss about the shear force and bending moment diagram. Now before starting this bending moment and shear force diagram, first of all we're going to discuss about the course objective of today's topic. Course objectives of today's topic is to determine the shear force and bending moment for different types of beam with different loading. Now after completion of this SFD and BMD, what we're going to learn on the completion of this chapter, students will able to calculate the shear force and bending moment in determinant beam for different loading conditions and insert shear force and bending moment diagram. So this is the outcome of today's topic. Introduction. While we are going to discuss about the shear force and bending moment diagram, we required some basic concepts of this for this shear force and bending moment diagram. So we have learned in first year engineering mechanics, that is types of supports. There are three types of supports normally found. First one is a roller support. Roller support is shown like this. A beam is supported over a triangle with a circular base which is fixed. So it is nothing but a roller support. Now while you are plotting the free-body diagram of this roller support, you know that roller supports offers only one unknown reaction, and that one is perpendicular to the base. So here I am going to show how we can draw the free-body diagram of this roller support. So this is the roller support. Three rollers are provided at the bottom and hatching line is shown at the base. Now what is the function of this type of support? You know that this support offers only one unknown reaction, and that one is perpendicular to the base. Now if you are rotating this support in any direction, so you rotate this roller support in 360 degree, so again you will get the only one unknown. So one unknown is that is perfect perpendicular to the base. So this is the perpendicular to the base. Now if this base makes an angle, any angle theta, then you know that this reaction will make an angle of 60 degree with the base. Correct? Now when such a reaction is there, we have the conditions of equilibrium, and that conditions of equilibrium are available along the x direction and y direction. So first of all, if you are going to consider this is the reaction R offered by this roller support, then this roller support is inclined, so it have the two components. So one component is acting vertically horizontal and one component is acting vertically upward. So the horizontal component of this reaction is considered as a R cos theta, and vertical component is considered as a R sin theta. So in this way you can rotate this support in any degree, so we'll get the two unknown. One component is cos and another one component is R sin theta. So this is the free body diagram of a beam, of a roller support. The next type of support we're going to discuss, that one is we are discussing about the types of supports, correct? Then how to draw the free body diagram of roll hinge support, that we have discussed. So second type of support is fixed support. So fixed support is nothing but three unknowns. One is vertically upward, one is horizontal, and one is moment. So this is known as a fixed support. So I think your concept will be clear about the how to draw the free body diagram of the roller support, how to draw the free body diagram of a hinge support, and how to draw the free body diagram of the fixed support. So fixed supports offers three unknowns. Next one is beam. What do you mean by beam? It is the horizontal member which carries the load from the floor or any assumed load which is transferred safely on the column is known as a beam. Then we are going to discuss about types of beam. There are normally four types of beams normally found in engineering mechanics. First one is a simply supported beam. What do you mean by simply supported beam? A beam which is supported over two supports at the end. That beam is known as a simply supported beam. This way we can show the simply supported beam. One support is at first end and another support is at the next end, last end, and the beam is supported different types of load depends upon the situation and condition. So this is nothing but a simply supported beam. The next type of beam is there. Next type of beam is cantilever beam. If one end of the beam is fixed and other end is free, then the beam is known as a cantilever beam. Such type of supports we have discussed. This type of supports offers a three unknown reactions. Is it clear, please? Okay. Then continuous beam. What do you mean by continuous beam? A beam is supported over more than two supports. Then that beam is known as a continuous beam. If the supports are more than two, that may be maximum anything, but that beam is known as a continuous beam. So for example, I have shown here a beam is raised over three supports. First support is a hinge support, second support is a roller support, third support is also as a roller support, and it is continuous. The supports may be number of, but the condition is that the beam should be supported over more than two supports. So that beam is known as a continuous beam. The next type of beam is there, that is compound beam. So what do you mean by compound beam? Here I have shown the diagram of the compound beam. If two beams are connected by the internal hinge, so this is the internal hinge. Let us consider this is A part of the beam and this is the B part of the beam. So A and B are the different beams. They are connected by the internal hinge. Then that beam is also known as a compound beam or the composite beam. Another condition is there, if one beam is raised over the another beam, then that this total arrangement of beam is known as a compound beam. So you treat first beam as a separate, you treat second beam as a separate. So the such a type of beam is known as a compound beam. So these are the types of compound beam or types of beam. Then types of load. We know that these types of supports we have discussed, loads we have discussed in engineering mechanics. So the first type of load is the point load. Point load is shown by the single arrow, and this point load is expressed in Newton or kilonewton. This is the diagram where beam is supported over two supports and it is subjected to load of P, but this P is expressed in kilonewton or Newton. This is known as a point load. Then second type of load is there, that is UDL. It is also known as a uniformly distributed load. So uniformly distributed load is shown like this. Now the intensity of loading is same throughout the beam or throughout where this loading is acting. That is known as a uniformly distributed load. Now uniformly distributed load is expressed in kilonewton per meter or Newton per meter. So first of all, we are going to discuss about how to convert this uniformly distributed load into the point load. So let us consider this UDL is acting over a span of L meter. L is expressed in here, in this case this L is expressed in meter. Okay. Then now you see here or how much distance this W is acting. This W is acting over a distance of L meter. So you know that the unit of UDL is kilonewton per meter. Kilonewton per meter. Now we want to convert this kilonewton per meter into the kilonewton. So you multiply it by the meter. If you are multiplying it by the meter, then meter get cancelled and remaining one is kilonewton. So you know that the kilonewton is the unit of point load. So what we have done here, so what may be the magnitude of the UDL? That magnitude of UDL is multiplied by the distance over which this UDL is acting. Then this is considered as a point load or magnitude of the point load. And what is the position of this point load? Point load is acting at the center of this UDL. So the center of UDL from the first end is L by 2 and the second end is L by 2. In short, we can say that this point load is acting perfectly center of the UDL. So in this way, we can easily convert this UDL into the point load. Then third type of load is there. That third type of load is known as a uniformly varying load. It is also known as a UVL. So what happens in the UVL? In the UVL, at one end the load is 0 and at other end the load is maximum. Such type of load is known as a uniformly varying load. So at which situation this force is created? You know that if the water tank is there and this water there is a vertical wall. On that vertical wall some pressure is applied by the water, so this water creates a triangular pressure. It is also known as a uniformly varying load. So the maximum load is at the base and minimum load is for example, I'm plotting the free body diagram of a water tank. So this is, let us consider this is the level of liquid stored in the water. Then if you want to draw the what is the load or pressure exerted by this liquid on the wall, then this is the reference line and this is the pressure created by the water. This is a uniformly varying load, where at top the intensity of load is 0 and here you'll get the maximum, depends upon the density of the unit weight of the water. So according to that one, we can easily calculate the uniformly varying load. So I have just told where this actual load is acting. Yeah, another one simple example of this uniformly varying load is a retaining wall. When a wall is constructed and on other side soil is raised or soil is filled, so soil will create a triangular pressure. It is also known as a uniformly varying load. Uniformly varying load is expressed in kilonewton per meter or newton per meter. The unit of UDL and the uniformly varying load UVL is same. Now, what is the difference between the first one? The intensity of the in UDL is same, but the intensity of UDL in the uniformly varying load is different. That is 0 at one end and maximum at the other end. Let us consider this is a simply supported beam over which this uniformly varying load is acting of magnitude W. Now, first of all, you try to convert this uniformly varying load into the point load. Then you consider triangular loading as a right angle triangle, and then you calculate the area of this right angle triangle. So you know that the area of right angle triangle is 1/2. Base you consider as a span over which this UDL is acting, and W you consider as a maximum intensity of the load. So this is the area of triangle. Area of triangle is nothing but the point load created by the uniformly varying load, and it is acting at the perfect centroid of this triangle. You know that the centroid of the triangle is acting 2/3 of L from the apex and 1/3 from the base. So in this way, we can easily convert uniformly varying load into the point load. So these are the some types of load. Bracket loading is also there, but bracket loading we are not going to discuss here. You know that the bracket loading. So conditions of equilibrium. You know that there are three conditions of equilibrium. So sigma fx is equal to 0. So algebraic addition of all the forces acting along the x direction is equal to 0. Second condition of equilibrium is there, that is sigma fy is equal to 0. Algebraic addition of all the forces acting along the vertical direction is equal to 0. So if these two conditions are satisfied by the beam, then the third condition of equilibrium is also there, that is sigma m is equal to 0. If any beam is subjected to any type of load and you take the moment of this external loading about any point, then that moment should be 0. If any beam is or any body is satisfying these three conditions of equilibrium, that is sigma fx, sigma f, and sigma m is equal to 0, then that beam is said to be in equilibrium. So these are the three conditions of equilibrium. Structural action of the beam. We know that while we are discussing about the shear force and bending moment, so these are the basic concepts required for the while you are plotting the shear force and bending moment diagram, and this basic concept is also required to calculate the support action. So I'm not going to read anything about this structural action, but here I want to say how to calculate the bending moment diagram and shear force diagram. While you are calculating the shear force and bending moment diagram, some sign conventions are there. So first of all, if a beam is there and the beam is supported or supported by two supports and it is subjected to vertically downward, we have discussed about the shear force and bending moment diagram, correct? So the moment which is acting or the beam in a hugging is considered as a negative and sagging is considered as a negative. Then shear force, we already discussed about the shear force. The shear force at any section of a beam is equal to the algebraic sum of forces perpendicular to the axis of the beam, either to the left or right of the section, is nothing but the shear force. What is bending moment? Bending moment is nothing but at any section of a beam is equal to the algebraic sum of the moment of all the forces either to the left or to the right of the section about the section. So this is nothing but the bending moment. Sign conventions for the SF and BM that we're going to discuss. If you have taken a section, first of all, this first A part indicate the sign convention for the shear force. If a section is taken and if you are coming from right hand side, downward is taken as a positive, and if you are coming from right to left, the upward is taken as a positive, and vice versa. So here normally upward is taken as a negative, downward is taken as a positive, uh, in the sense if you are coming from right to left. Then sign conventions for the bending moment. Anti-clockwise moment is taken as a positive, clockwise moment is taken as a negative if you are coming from right to left. And if you are moving from left to right, then the clockwise moment is taken as a positive and anti-clockwise moment is taken as a negative. So these are some sign conventions used in the while you are discussing the shear force and bending moment diagram. Then, while you are calculating the shear force and bending moment diagram, some basic concepts are required. So, if you are try to draw the uh, shear force and bending moment diagram, then directly it is related to the degree of curve. If a point load is acting on the beam, if suppose if you are considering this as a point load, and if suppose it is a beam and it is subjected to the point load at any distance, this is the point load. Then if a point load is acting on the beam, then degree of curve for the shear force is 0, means you will get the straight line but it is horizontal, and the curve, first degree curve, will get that is a straight line but it is inclined. If a beam is subjected to UDL, uniformly distributed load, then you will get the first degree, means you will get the shear force diagram, you will get the straight line but it is inclined, and parabolic curve, that is also known as a second degree curve for this bending moment. And if a beam is subjected to uniformly varying load, then for shear force diagram you will get the second degree of curve, it is also known as a parabolic curve, and you will get the for the bending moment it is a cubic parabolic curve or third degree curve. So this is the degree of curve varying according to the types of load which is acting on the beam. So today we're going to discuss about the how to draw the shear force and bending moment diagram. A simply supported beam subjected to 3-point load. First end is hinge and second one is roller support. First of all, while you are solving such type of problems, first of all you try to draw the free body diagram. We know that the hinge support offers two unknown reactions. One is horizontal towards right and one is vertically upward. and at E there is a only a roller support is there, so only one unknown is there, and that is perfect perpendicular to the base. So this is the free body diagram of the given beam. Then you show the load as it is acting on the beam and apply the sigma fx is equal to 0. On this beam only one reaction is acting towards right, that is HA. So to balance this HA, there is no any other forces acting on this beam in horizontal direction, so indirectly HA becomes 0. The second condition of equilibrium, sigma Fy is equal to 0. So here two forces are acting, three forces are acting vertically downward, that is 40, 70 and 50, and two forces are acting vertically upward. So here one force is acting vertically downward, it is also subjected to vertically downward at point C and vertically downward at point B. Okay, so this is a 50 kilonewton, this is 70 kilonewton, and this is 40 kilonewton, correct? Now this is the free body diagram of the given beam. You show the distances also here. You apply sigma Fy is equal to 0, Va upward minus 50 minus 70 minus 40 plus Ve is equal to 0. So indirectly Va plus Ve is equal to 160. You treat this as equation number 1 and apply the third condition of equilibrium, sigma m is equal to 0. So now which point you will select as a moment center where maximum unknown reactions are there, support reactions are there, at that point you select as a moment center. So here I have selected the moment center as A. So you take the moment of all the forces acting on this beam about a point A. So write the equation of bending moment. Here I have taken a moment due to VE. What is the perpendicular distance of VE from A? This is the perpendicular distance of VE from A. So VE into 2 plus 2 plus 2 plus 2, that is 8. So VE into 8, and it will create a anti-clockwise moment. We know that the anti-clockwise moment is taken as a positive. That's why I have considered here VE into 8 as a positive. Then moment created by this 40, it will create some moment in a clockwise direction, and this is the perpendicular distance of this 40 kilonewton, correct? So 40 into 6, it will create a clockwise moment. That's why the sign is taken as a negative. The second force is there, that is 70 kilonewton. 70 also creates a moment about A in a clockwise direction, and this is the perpendicular distance of this 70 kilonewton. 70 into 4, it will create a clockwise moment. That's why the sign is negative. Then the third force is there, it will create a moment in a clockwise direction. So VA 50 into perpendicular distance is 2. It will create some moment in a clockwise direction. So your sign should be negative, is equal to 0, because HA and VA is acting at A and its perpendicular distance from A is 0. That's why the moment due to HA and VA is not considered. By solving this equation, you will get the value of VE, and we get VE is equal to 77.5 kilonewton. The sign is positive, that means assumed direction of VE is correct. VE we have assumed as vertically upward, that's why the sign is positive. Then substitute this value of VE in the equation number 1, we will get VE is equal to 82.5 kilonewton. So in this way we can easily calculate the support actions. Once we know the support action, then the next target is to draw the shear force diagram. So calculation of SFD. While we are calculating the SFD, you select a point where point load is acting, and take the two section at that point load. One is on the right hand side part of the section, and another one is the left hand side of that section. Okay, so here I have considered a first section, this at VE. We know the value of VE. So shear force at E, just right. Is there any force acting on the right hand side? No, there is no any force acting on the right hand side of this E. That's why the shear force at E is equal to 0. Then shear force at E but left side. So there is one force is acting, that is V, and vertically upward. So here we'll get the shear force at E just left is minus 77.5. Minus sign, why? Because it is acting vertically upward. Then second section you take, section at D. Here we are taking the section. So while you are taking the section at D, shear force at D, just right. How many forces are acting at D right? Only one force is acting, VE, towards on the right hand side of this section. So here shear force at D, here you will get the value. Shear force at D is equal to minus 77.5. Same, only one reaction is there, vertically upward, and that is VE. Then shear force at D, just left. How many forces are acting? Two forces are acting. One is V and another one is 40. V is minus and 40 is downward, so it is plus. So shear force at D, just left, is minus 77.5 plus 40. You will get it as a minus 37.5. Similarly, we can take the section at C and B. If you are taking a section at C, then shear force at C, just right of the section, two forces are acting, V and 40. One is vertically upward, one is vertically downward. So VE vertically upward is taken as a negative, downward is taken as a positive. Here I have written here shear force at C, just right, is minus 77.5 plus 40 is equal to minus 37.5. Then shear force at C, just left, is equal to, so shear force at C, just left, is this value. So here here you will get the three forces. One is VE vertically upward, 40 vertically downward, 70 vertically downward. I have written here, and you will get the shear force at C, just left, is equal to minus 32.5. Similarly, you can calculate the shear force at B, just right and left, and shear force at just A, right and left. So in this way, we will get the shear force diagram. Then once we know the calculation of shear force and bending, shear force at A, B, C, D and E, just right and left, then you try to draw the shear force diagram. For that purpose, you select a baseline. So it is also known as, this is the baseline. It is also known as a reference line. Below the reference line, shear force is taken as a negative. Above the reference line, shear force is taken as a positive. The shear force at E, just right, is 0. Shear force at just E, just left, is minus 77.5. It is constant up to the D. Shear force at D, just left, is minus 37.5. So it is minus 37.5. It is constant up to the point C, right. Shear force at D, just left, C, just left, is equal to plus 32.5. So you will get the plus 32.5. It is constant up to the B, right. Then shear force at B, just left, we will get it as 82.5 positive. It is constant up to the A, right, and then the shear force at A, right, left, is 0. Here some mistakes is there. So instead of B, here it is A. Okay, so in this way you can easily draw the shear force diagram. Then we're going to discuss how to draw the bending moment diagram from the loading diagram. First of all, you show the beam as it is. Bending moment at E. So you take the, we know that this is the beam. It is subjected to three loads at equal distances, 2 meter, 2 meter and 2 meter. So I think VE is equal to 77.5. Then last it is 40 kilonewton. Then 70 kilonewton. And last one is 50 kilonewton. Correct. And at A, support action is there. Correct. So 50 minus 70 minus 40 will get this VA here. So you start from the right side. What is the bending moment at E? This is the E point. What is bending moment at E? Is there any force acting on the right hand side of E? Not a single force is acting on the right hand side of the beam. So that bending moment at E is equal to 0. So bending moment at D. How many forces are acting on the right hand side of this D? Only one force is there, that is 77.5. 77.5 into the perpendicular distance of this 77 is 2 meter. So 77.5 into 2, and it will create a moment in anti-clockwise direction. That's why it is taken as a positive. 77.5 into 2. Then bending moment at a C. This is the point C. So you take the next section at a C. How many forces are acting on the right hand side of this section? Two forces. One is 77.5 and another one is 40. So this 77.5 creates an anti-clockwise moment, and 40 will create a clockwise moment. Correct? So 77.5 into 4 perpendicular distance plus 40 into 2 is the perpendicular distance of this 40 from C. So 44 into 2, here you will get the calculation of bending moment at C. You will get it as a positive 230. Then bending moment at B. How many forces are acting on the right hand side of this B? That's 77.5, 40 and 70 are the three forces acting on the right hand side. So this 77.5 creates anti-clockwise positive, 40 clockwise negative, 70 clockwise negative. So here I have written here 77.5 into perpendicular distance is 6, that is sign is positive because anti-clockwise. 40 into 4, 40 into 4, 4 is a perpendicular distance of 40 from A, and it will create a clockwise, that's why the sign is negative. Then 70 also creates a clockwise moment, it is negative, and perpendicular distance is 2, so we'll get it as a positive. Then bending moment at A is equal to, so if you are taking a section at A, how many forces are acting on the right hand side of this A? So VE, 40, 70 and 50. So these are the four forces acting on the right hand side of A. So 77.5 into A, 8 is the perpendicular distance of this 77.5. Then minus 40 into perpendicular distance is 6, minus 70 into 4, perpendicular distance is 4, it will create a clockwise, that's why sign is negative. Then moment created by the 50 into 2, perpendicular distance of this 50 from A is 2, that's why it is 50 into 2 is equal to 0. So bending moment at E and A you will get as a 0. So this is the bending moment diagram. So you will get the straight line. Bending moment at E is 0, bending moment at D is positive, then bending moment at B is bending moment at C is 230, this is again straight line. Bending moment at B is 165, again straight line, and then bending moment at A is 0. Okay, so this is a straight line because it is subjected to point loss. So in this way you can easily calculate the shear force and bending moment diagram. So in the next lecture we are going to discuss about the how to draw the shear force and bending moment diagram of a simply supported beam subjected to UDL. And the next one we are going to discuss about the how to draw the shear force and bending moment diagram of a simply supported beam subjected to uniformly varying load. And the next point we're going to discuss about the how to draw the shear force and bending moment diagram for uniformly varying load. And last one, how to draw the shear force and bending moment diagram for the simply supported beam subjected to the couple. Okay, I think this next we're going to cover in the next topic. Thank you very much. If any difficulty, you are free to contact. Here I have given the contact number. Thank you very much.